This afternoon is Valerii Vinokur from Argonne National Laboratory, and he will talk about vortex spinning, statics, and dynamics.
Good afternoon. And first of all, I would like to thank organizers and first of all, Elena and Leonid for having me here. Well, it's a pleasure to talk about what I believe is one of the most appealing parts of the vortex physics in front of this audience. But, well, immediate warning, please switch gears immediately because you're not going to hear anything even close to the match to what you've heard before. I mean, neither in terms of beautiful math, neither, beautiful experiment, which you've seen in just like preceding wonderful talk. This is, because this is the field where developed mathematical methods do not exist. And, for me it was quite lucky because with my mathematical skills, which do not go beyond junior high algebra, this was just a wonderful niche to work on. And so this was the field which was led really by great people whose intuition and guess allowed to make a great progress. And so we were quite fair to choose this motto for all this activity. This is this is going to be the history or display of hypotheses and guesses. Indeed, no math at all, just bare statements. And all the recent wonderful math came thanks to Leonid Berland, whose work whose talk I will, he will be giving his talk tomorrow. I'll just say a few words about, what was discovered there. So, well, let's start. This is not the original handwriting, but it's the original board, and it was written by Ginzburg hand, but a little bit afterwards, after 1950, when this equation was written for the first time. And almost immediately this became, well, I shouldn't talk about this, in this audience, of course, but because you know that this became one of the most productive and popular equations in physics of the second half of past century, and probably one of the most popular in mathematical physics as well. One thing, now everybody is so used to that it takes quite an effort to realize how pioneering it was at the time, and the pioneering was this term here. Because it has already been said, this morning, that this is extension, that Ginzburg-Landau equation, and this is equations, are the extension of Landau theory of second phase transition, and this is absolutely true. And it was said that the other parameter is a quantum mechanical quantity. This was a pioneering thing to do. But what was enormous at the time step forward to realize that since the other parameter is quantum mechanical, since this is quantum mechanical theory, then this theory is obliged to be gauge invariant. And that's why this term appeared, and this is a difference from the standard Landau second-order transition theory. And it immediately gave this small addition, immediately gave all this richness of the superconducting behaviors and this equation behavior which we heard today in the previous talks. What is important in this equation? This equation is written in its physical form the way it appeared, for the first time. And what is wonderful about this equation is that that there are two length parameters there. One is responsible for electromagnetic behavior, and another one is responsible for quantum mechanical behavior. This is London penetration depth, and this is well, on a quantum mechanical language, this is basically the size of the Cooper pair. And these two parameters and the interrelation between them define all the physics of superconductivity. And the most wonderful thing is, again, this is a little bit of physics, that they diverge in the same manner as temperature approaches the temperature of the superconducting transition. And this means that if you make the ratio of these two quantities, then temperature scales out and you get what you call material parameter, which is the only parameter which determines the behavior of this equation. Then you can, rescaling this length out, you can immediately come to what is called natural units for Ginzburg-Landau equation and arrive to the form which is very familiar to you, dimensionless form, and the behavior of the equation, again, is determined by this parameter. And as I said, this equation became one of the most popular in the physics of the second part of 20th century. It was immediately borrowed by many others fields, like field theory, particle physics, and, well, every time it was immediately getting new and fancy names, Higgs, abelian Higgs model, or Salam model for weak interactions. This is basically nothing but Ginzburg-Landau equation. But of course, it's very useful for grant hunting purposes. Use now probably non-abelian Higgs model will do. Now we're coming to vortices. So one of the most telling features of Ginzburg-Landau equation is that it can have singular solutions. And these singular solutions were for Ginzburg-Landau equation, which we call now vortices or Abrikosov vortices, appeared only in 1957, but they were actually predicted and discovered in 1949 by one of the greatest minds of last century physics, Lars Ansager. Actually, it was quite bitter time for him because at that time he had already stopped publishing because he knew that nobody will understand anything anyway. This discovery of vortices came at this was a beautiful time when it was, when everything was written at the conferences, not just the talks, but even the comments on the talk. And Ansager's prediction and actually absolutely comprehensive physics of what vortices are were given as a comment to the talk of Henk Gorter. This actually opened the way to Abrikosov publication, not to his original work, but to his publication. Well, I'm not going to dwell on it, too much because this you know better than me. But one of the important things which was done, according to the, let's say, how should we call it, myth or, legend, the discovery was made in as early as in 1952, but was published only in 1957. Well, there is some truth in it, and the truth is that after Abrikosov found his solution in terms of theta function, it's a beautiful function, and the only thing which is not quite beautiful about it is that it has singularities. Now we know that, the singularities are just vortices, but at that time it was hard to believe that nice and smooth equation with the continuous coefficients can produce something as ugly as the singularities. Well, and the fact that the singularities were arranged into the square lattice didn't help much. It still were ugly singularities. Only when it was realized, when Ansager and then Feynman work has become known in Soviet Union, only then it was realized what this singularity do mean, and Abrikosov published his famous work, which won him Nobel Prize. Okay, now we are basically almost done with all the math. I just reproduce, okay, the things, how we understand what vortices are now, because we understand that this is the singularity around which the phase acquires 2 pi if we go around each singularity, and that each singularity is surrounded by encircling supercurrents. This is where the name vortices come from. And then now, coming back to what, okay, and vortices indeed is a very telling thing because they allow to classify superconductivity into different classes. So we know that the superconductivity where vortices attract each other and they actually collapse on top of each other, they are called N vortices, or if you want to, okay, fancy name from the field theory, there is a name N-nimbus strings. Then there is a region, this is called first type superconductivity. Then there is a second type superconductivity. This is where vortices repel each other, where this material parameter is large. And then, well, again, it was discovered for quite some time ago by, at that time, young guy, Eugen Bogomolny, who was, okay, particle physicist from Ginzburg-Landau Institute. He realized that if kappa material parameter is exactly 1 over square root of 2, then Ginzburg-Landau equation can be decoupled into 2 equations of the first order, and then the solution has very special properties, which now we call supersymmetry. And there was a just outburst of the interest to this, what we can call now critical superconductors. There was an awful lot of beautiful works and basically mathematical works around this critical Bogomolny point. And what we found quite recently was that if we take a multi-band superconductor, a superconductor which has more than one component, this is exactly what we have heard, okay, this morning. So then in this kind of superconductors, this Bogomolny point actually broadens into the wide domain where this critical superconductivity, which is the one more kind of superconductivity, does exist. And so if we say that in first order superconductors, vortices are, okay, collapsing on top of each other, repel each other, making a vortex lattice in type 2 superconductors. In critical superconductors, the vortex state is infinitely degenerate with respect to configuration of vortices. Well, interestingly enough, that, okay, that on a rigorously mathematical language, these theorems were proved about this vortex stability in both cases. Okay, not, okay, very recently actually. Okay, now we've done with the beautiful math and, okay, and go to the terror of just simple guesses, because not much can be done about the really random systems. So what we can do first, we just remind ourselves what vortices are, that there is a, okay, long length where, okay, currents disappear, very short normal core. And then if we remember that, we immediately realize that vortices are nothing but hydrodynamics objects. And when we're talking about vortices, we can talk almost exclusively using the language of hydrodynamics. And then everything becomes simple and easy. So, first of all, we immediately realize that if we are going to bend vortex, to deform it, it means that we just deform the distribution of currents. and we have to spend some energy for doing this, and it means that we can assign some energy to vortex line, which is just the linear tension of the vortex. We can find immediately what it is, and then just reducing our task and making it real easy, we can talk about vortices like about elastic lines which interact with each other by this hydrodynamic way. But other than that, they behave just like flexible lines, and we can very easily, this is the free energy, then this is the term in the free energy responsible for the bending of the vortex line, deforming it, of course, in the linear approximation. Otherwise, the formula would have been a little bit more complicated. And then we can very easily construct statistical physics of vortex lines at finite temperature. This basically was done. The existence of Abrikosov lattice was justified once again. All the elastic properties of Abrikosov lattice, including all the elastic moduli, were calculated. A lot of beautiful things were done. And again, using this hydrodynamic approach, we can immediately understand why vortex lattice forms, because vortices repel each other. This is just Magnus force. And if we put these vortices in the box, they repel each other, but they are restricted to the box, so they arrange themselves periodically to minimize their energy. Now, well, some of you who are, it's good to see so many young people, and therefore not everybody remembers that it was, again, a revival of enthusiasm concerning superconductivity when high-temperature superconductors were discovered, and it was a lot of enthusiasm among the people doing superconductivity because everybody was waiting that probably tomorrow, too much if it's going to happen in a week, every household will have superconducting refrigerators, stove, and things like that. So it was a lot of, as I said, a lot of enthusiasm. It was only one thing to cool it down. It appeared that these vortices, which of course are very useful because it is just these vortices which make superconductivity stable with respect to high field, the same nasty vortices immediately start to move as soon as you apply current. Then they dissipate energy, and then your beautiful superconductor immediately turns into a metal, maybe a good metal, but still metal, not superconductor. Because you apply current, you dissipate energy because of the vortex motion, and then it appeared that the pinning, which was pretty strong in conventional superconductors, is actually quite not that effective as soon as you are talking about high temperature superconductors, which is no wonder because temperature is high, thermal fluctuations are strong, and pinning centers becomes just smoothened down. So this immediately revived the interest to pinning because pinning is just something to stop vortices from motion and recover superconducting properties. And then a theory of collective pinning created by Larkin quite some time before discovery high temperature superconductivity was recalled again. So the idea, the first idea was the realization that in every superconductor, real superconductor, just the piece of junk which you find not in the street but in the laboratory. Of course, it does contain impurities, so it's not homogeneous, and then fluctuations in the distribution of these inhomogeneities are going to pin. And what is important that this pinning occurs in a sort of collective way because one inhomogeneity, one impurity may be not strong enough to pin vortex line when you apply sort of substantial current. And then it was immediately realized by Larkin that because of this collective effect, the pinning should not exist at all whatsoever. And the consideration was very simple. Since pinning occurs only due to fluctuations in the impurity density, Then, of course, if you calculate some pinning force, which acts on the vortex line due to these fluctuations, this force should scale like square root of the length, right? Just statistical summation, like random walk. If you have plus and minus walking energy, okay, then it's going to give you just, okay, square root of the number of the steps. But then, immediately, when you apply the force, which exerts some force on the vortex, just apply current, and this force, of course, is going to be proportional to the length of the segment in question. And then, of course, as soon as the length is large enough, it's going to dominate over the pinning force, well, and then there is no pinning whatsoever. But it was experimentally, so it was immediately a paradox, and Larkin almost immediately resolved, okay, this enigma in a beautiful way. He realized that a vortex line has to be split into the segments which are pinned more or less independently. Then, of course, you do this statistical summation at this independent segment, which now we call, and this characteristic length we now call Larkin length. But then, on the large scale, you recover linear dependence of the pinning force upon the length. And then, immediately, you realize that, yeah, the pinning is recovered, and then you have to just balance, okay, the pinning force and the applied force, and if the spinning constants are strong enough, then, of course, the vortex would remain pinned, and then he made an estimate for the critical current, which appeared to be in a very good agreement in what was found then in high-temperature superconductors. Well, this theory can be refined, but the idea is basically the same. You make a very simple balance just on the level of the, let's say, dimensional estimates, and then you find the value of the critical current. One interesting thing, which is, okay, again, important for practical applications, was to realize that the softer the line or the softer the vortex lattice, the better it can be pinned, well, which is not, okay, that surprising after the fact, after it was pronounced for the first time, because, of course, it can adjust itself much better than rigid stick. The rigid stick in a random potential is not pinned at all because all the positions statistically are equivalent. But the flexible line or flexible lattice can adjust to the particular relief depending on the position where it is. Well, this is, again, what we've seen in the previous slide, where the formulas given for the vortex line. It can be generalized onto the vortex lattice. Actually, nothing changes. Conceptually, we have only just the dimensionality of the different parameters different. And this was quite successful theory. It beautifully works, and it works so beautifully that it was tempting to apply it beyond the physics, for example, to a social life and history. And then splitting up Roman Empire can be immediately seen as a competition between local pinning force and long-range interactions, okay, keeping empire together. As soon as the local forces became stronger than the long-range interaction, we immediately got the modern Europe. Okay. Next. But of course, what was the most interesting was vortex dynamics. And out of the vortex dynamics, the most interesting was its slow thermally activated motion, which occurs at low temperature and small applied force when the vortex line or vortex lattice, whatever you consider, should move very slowly with a, big difficulties overcoming potential barriers created by the pinning potential. Now, what we knew by the time we came to investigations of the dynamic of the vortex lattice about the dynamics was the law, actually Ohm's law, which is as unbreakable and as fundamental as the, for example, conservation of energy. This is what we learn as soon as we start to learn physics, even if we just learn only electrotechnique or something like that. Okay, Ohm's law. What does it tell us? It tells that if we have a physical system, we apply the force, and then the reaction of the system is proportional to the applied force. Very simple, very fundamental. And why it is very fundamental? Because this is the consequence of the fact that we do have a ground state of the system. Okay, my friend Leonid warned me that this is sort of forbidden word, ground state, because mathematicians are not supposed to understand what does it mean. Okay, so this is the state which you will obtain by minimizing the function of the free energy. So, borrowing the name from quantum mechanics, it's called ground state. So, okay, so the basic assumption is that every system does have its state of minimal energy. If it's minimum, then the dependence on any parameter which takes the system away from this minimal energy state, ground state, so the shape is of the energy is going to be parabolic there. It means that when you apply external force, the distortion of this parabola is linear, and this is where the linear restoring force comes from. So this is, I mean, and since all the systems do have their ground states, then, okay, we have all these linear laws, Fourier, Ohm, fix, okay, which regulate transport of whatever we can find in the nature. That's made this, okay, vortex physics so wonderful, because as soon as we start to try to investigate this thermally activated motion at low temperature and low force, we immediately find that this motion is not ohmic anymore. Sad, but okay, but it looks like this is the fact, so even unbreakable laws of nature can sometimes fail. Well, we can try to see where does it coming from. Well, of course, I'm not daring enough to pronounce this beautiful rhymes on its original language with my rusty French, but this is the only way the vortex dynamics can be considered. Only if we are not serious enough. So, and young enough. Okay, so this is, okay, now this is what comes instead of Ginzburg-Landau functional, more complicated if now we remember that vortices are just elastic lines, and therefore this is the free energy of the elastic line, this is the elastic energy, this is spinning energy, which is all the trouble, because it's just the random function, and the only thing which we know about it at best is its correlation function, which we can take Gaussian, of course, to make our life easier, because otherwise there is no hope at all. And then, well, it's not quite Hamiltonian, because we want to add some gain in the energy due to applied force, because we're going to construct some kind of dynamics. And that's what we're going to do, since, well, of course, we know how to solve this problem. And it's just to demonstrate that sometimes, okay, even physicists look into some clever books and, okay, and study some math. So what we're supposed to do, of course, is to take this Hamiltonian, to write down what is called generating functional in the field theory, do some average over disorder, and after this average, to obtain immediately what is called non-local field theory, which is unsolvable. So therefore, instead, we have to do, okay, the following. Just take these three terms, since we're not serious, and make a simple estimate what they are. Well, it's simple. Again, since some people cannot go, as I said, beyond the junior high algebra, then, okay, we know that instead of derivative, we have to take some function divided by the, okay, by the characteristic length. Instead of integral, again, we have to take, well, the volume, meaning characteristic length times to the power of dimensionality. A little bit more complicated this term, but we can make, okay, this kind of hypothesis saying that this is some scaling of the characteristical length. And then, again, this is very simple. And then what we have to do, because we're still, okay, not serious, well, one more scaling hypothesis, which tells us that if we do have some energies for the elastic string, for concreteness, we can be talking about elastic string here, that some minimal energy positions which elastic string assume in the random potential scale in this way. So this is characteristic displacement, this is characteristic length, this is hypothesis, and then, again, being just very loose in what we're doing with all this mud, just assume that all these three terms, when if give equal contribution to formation of this ground state or minimal energy. After that, we do have just, okay, two equations with two unknown quantities, which are characteristic length and characteristic scale of the fluctuating segment. And then we can find immediately the energy of this fluctuating segment and construct the velocity of thermally expression for the thermal activated velocity. I'll show you in a minute how to do it. Okay, this is just repetition, so let's go through this. But now I would like to make the step aside. I showed you some scaling before. Okay, let's take it here. There are some powers. And if we just do the calculations, we can find out that these powers here in 2 dimensions, for one-dimensional string in 2 dimensions, okay, this power is going to be 1/3 and this is going to be 2/3. And we can immediately recognize where we could have seen these powers before. And we've seen these powers in Kolmogorov's theory of turbulence. This is exactly the powers which appear there. And then we can try to understand how these powers appear. And indeed, if we do a little bit more refined math, and and apply to this our Hamiltonian, which is called transfer matrix technique, and calculate this energy, the energy of the string as function of its one free end. Suppose we fixed one end of the elastic string and let it move and let another one move freely. Then we can immediately see that the equation, that we can write this kind of equation for the energy of the string as function of the position of its end, and you can immediately recognize Berger's equation here. Well, if you take just derivative with respect to u and then introduce new variable there, then it will be immediately Berger's equation, and one can immediately demonstrate that this Berger's equation shows exactly this kind of scaling. This is one of the beauties, by the way, of the vortex physics, because it's just like a focal point of all the possible branches and areas, both in physics and I believe in math as well. Okay. And now we can try to make one more step again back in the site and understand how can we come indeed to this kind of behavior, this highly nonlinear behavior. So what we can do on a, well, I wouldn't say mathematical level of rigor, but okay, sort of 1% of it, is to derive this scaling laws for the thermodynamics of the elastic string or vortex lattice in the random potential. But it's okay, but the way to dynamics is okay, like to the stars. It's still far away. So let's try to see how we can get dynamics out of our knowledge of the statistical physics of the elastic line. So let's see how this elastic line is going to do. Okay, nowadays it's very easy to do. We can make numerical simulations on computer, but at all times, okay, it was necessary just imagine it. And if we, okay, so how the elastic string moves, it makes these jumps, throwing large segment of itself into the next volley, energy volley favored by the applied force. And okay, and this throwing occurs under the action of thermal fluctuations. And then we can immediately realize that this motion can be viewed in the following way. So this is just okay, a sketch of the string in its original position. Then part of it jumps into the next one. And then we can make it a superposition of the following ones. Just the original position plus some vortex loop. Then these two parts annihilate and we'll get something like that. So then we can immediately view, and this is just, okay, nothing rigorous in it, okay, just graphics and imagination. We can view the motion of the, we can view thermally activated motion of the elastic string like creation a new phase of liquid, for example, from the vapor, like formation droplets of the liquid out of the vapor. This, okay, this round thing somehow is very, okay, looks like the droplet, right? And then what we can do, we can immediately apply to this motion all the power of not mathematical theory, but again physical theory of metastable, of kinetic of the first order transition. Because this theory, again, not on a mathematical level of rigor, was developed, okay, first it appeared in 1943, I believe, in connection with the investigations related to nuclear weapon. So it's sad to say, but this is where it came from, this theory, and the fact that we have more or less effectively acting nuclear weapon is sort of evidence that this theory works pretty well. I mean, a theory of the metastable decay in the first order phase transition. So basically what it tells us that if we have free energy which depends on some parameter, then the critical activation energy which controls and governs thermally activated behavior is critical energy corresponding its maximum. So if we use this and then we know how to find the energy for this, okay, bendings of the vortex line, we solved our problem, and then we find this highly nonlinear motion of the vortex line, which immediately contradicts to all what we know from the irreversibility thermodynamics. Actually, this can be written in a very simple way if we just start to think about the behavior of the random systems which now called with the generic name glasses. So what glasses are, and this topic became very popular because basically all the real systems in the world are in a sense glasses, is that these are systems which have very wide distribution. This concept was introduced by Phil Anderson, very wide distribution of energy barriers which control behavior of the system. Now we know that if we have energy barrier, then the time to overcome the barrier, E, is just like this. This is just the Arrhenius formula. And then we can immediately conclude that there is a law of relaxation in the glassy systems, which we call T-log-T law, and it's very easy to understand where it's coming from, even without any derivation. And the consideration is very simple. If the energy, okay, this is the time which is necessary to overcome this barrier E. We just inverted this formula, right? So if the barrier, which we're interested in, is much higher than that, then the system knows nothing about it because we have to wait some time till the system is going to see it. But if the barrier is much smaller than this one, then it was overcome long ago, and now we can forget about it. So those are the only barriers which are relevant for the relaxation of the random system. And then, if we just use our scaling formula and combine it with this T-log-T formula, we immediately get the formula for the rate of the motion of the vortex line. Well, if we convert this formula for, let's say, something what we can measure, for example, for relaxation of the magnetization of superconductors, which we can indeed measure, then we can write down this formula, and it's interesting that this formula was indeed discovered experimentally. It took just the patience of young people. One of them was at that time at Argonne and another one in Sweden, who just decided that they're patient enough to sit 19 hours without any break in the lab, because to catch this logarithmic dependence experimentally at that time was very difficult. And now we are much more, let's say, sophisticated and skilled, but like 25 years ago it was hard. Okay, well, and as usual, okay, all the wonderful phenomena are first discovered by poets rather than physicists and mathematicians who can give them absolutely, again, beautiful expression. So it looks like what we call now vortex creep was discovered in the late Tokugawa period in Japan. Okay, move on. Now there is, okay, another thing. Since actually the goal of all this research and the grants given were given not just for the beauty of it, but to discover efficient mechanisms for pinning, the idea was that if we can make the pinning site as a cylinder, and the consideration was that this way we can match geometrical form of the defect and of the vortex line, then we're going to have pinning which is going to be strong. This hopes partly, let's say, justified themselves. Indeed, it was some increase of the critical current, but the most beautiful outcome was not that, but the beautiful outcome was that it was realized once again that statistical mechanics of vortex lines is equivalent, actually it's exact mathematical mapping between statistical mechanics and vortex lines and quantum mechanics of two-dimensional particles. That's why, okay, it was really enjoyable to listen to the previous talk where this some kind of correspondence between classical mechanics and quantum mechanics was also explored. So this is exact mapping, and this mapping found out, manifested itself in the following formula. One can calculate what will be the rate with which vortex line actually decouples itself from this linear defect. This is this formula. Well, But what is beautiful about it, or interesting, is, okay, first that this formula was observed experimentally, but the second is that exactly this formula, but with the just accuracy of notation, was also observed experimentally in a purely quantum mechanical phenomenon, which is called ionization. The ionization, or, okay, the formula for particles leaving the atom under the action of strong electric field. Okay, now the time is running short. I have to, okay, to come to the end. But there is one thing which I will try to briefly mention to you, which is the following. Vortices, okay, came with absolutely new phenomenon, which can be called disorder-induced phase transition. Actually, this notion now is called quantum phase transition, and this is the way where phase transition is achieved not by changing temperature, but by changing some other parameter. So vortices appeared a beautiful system which actually offered the laboratory to investigate these quantum phase transitions by changing disorder. So we can melt vortex lattice not only increasing temperature, but by changing temperature. So this is the line. This is the line of this disorder-induced melting of the vortex lattice, and this is which continuously goes into the line of the usual melting of the vortex lattice due to temperature. And even more wonderful phenomenon which was observed in dynamics. It was discovered that, okay, that this melting can be realized by motion of the vortex lattice. Namely, if you drive vortex lattice hard enough so that, okay, the disorder is almost unimportant. Let's see if it's going to work. No, well, actually not, then I tell you, and it will be faster. So if you drive lattice here, then the lattice moves as a whole, and here it looks like just isolated springs. And this is the motion of the, okay, molten vortex lattice. Let's see if I can make it. No. Okay. Pity. Okay, this is the summary of new physics which was discovered, okay, with the help of the vortex lattice. And now I'm coming to the, okay, to the most recent developments, thanks to, okay, to Leonid, who was insistent enough. It was found out that if we have this, okay, the system, which consists of this many, okay, cylinder just stuffed with these columnar defects, small holes, then what forms is not the expected smooth distribution of the vortex lines along the volume, but this structure of very well, okay, pronounced domain, nested subdomains, which are characterized by different discrete filling of this, okay, of these holes with vortex lines. And this came absolutely unexpected, but, well, Leonid is going to talk about this in more beautiful mathematical details tomorrow. But what I would like, okay, to talk about is the fact that this beautiful phenomenon, of course, after it was discovered, can be understood from the very simple considerations. There are always certain ways of, okay, of presenting the same fact, okay, in a different way. And basically, this, what can be called phase separation in one terminology, can be viewed as the proof of the existence of the solitonic solution in Ginzburg-Landau equation in 2 dimensions. So, okay, you know that there are several nonlinear equations which allow for non-trivial solution, which are called solitons, just, okay, this kind of formation This is just sine-Gordon equation. And basically what we've seen, talking about this separation of the vortex phases with different filling factor, can be illustrated by this simple mechanical model which was used to, for example, to illustrate Arnold's catastrophe theory. Actually, this was the device by which this was demonstrated by his students. Suppose we have this, sort of flexible and elastic ruler, and we start, we put it in the vise and start to compress it. First it yields a little bit, but then it loses its stability and makes something like this. Well-known thing. Now, let's assume that except for this device, we have also pronounced washboard potential to which we press our ruler. So we have potential wells or favorable position for this ruler. Now, let's start to compress it. First it yields, but then when it comes to instability, what it forms is this. It's not going to form this dome-like, continuous shape because it prefers to lie partly in this potential minima due to external potential. This appears to be more energetically favorable. And this is exactly what corresponds our discrete structure of domains. Instead of continuous distribution in vortex density, we have well-pronounced terraces of the constant vortex density and pronounced nested structure of domains. So this is, last news, I believe, in the vortex physics subject to disorder. And I believe that basically this was one of the first analytical results obtained in in this area. This is why it is so interesting. So let me stop here. There is no conclusion, I hope, because all the things is just on the way and comes into this new era when we can really apply analytical methods. So thank you very much for your attention.
Are there questions?